Morning. Okay, once more into the breach. Isn't that some famous quote? Shakespeare or something? No? All right, well, welcome back. What's happening? Everyone's getting closer to the front, or did we just lose everyone in the back? Is that what's going on? Yeah. All right, so last time we've lost some students. Yes, we have. Yes, we have. So last time we were talking about composite functions, right? And today we're going to do one-to-one functions and inverse functions. Next class, we start the exponential functions. So I have the notes up there on the board. Pardon me? No, they're very different, actually. It's all about where the variable appears. So in a quadratic, the variable is down on the bottom. And with an exponential, the variable is in the exponent. So, yeah, we'll see.
Oh, I get you.
Yeah. All right, so you ready? Yeah? We're going to talk about one-to-one functions. So let me remind you, all right, recall that when we first defined what a function is, right, we kind of did it with a picture. We said, all right, what's going to happen here is you have values and they get sent over here through some function f. And to be a function, the condition was that for each input, we have exactly one output, right? Each input has exactly one output. So that would have to go to one place. Now you could have this happen. You could have this go here as well, as long as for each input you go to one place. Nothing about a function says that you can't have 2 points here go to the same place. Right? This is okay in terms of being a function. What we're going to talk about today is an additional condition that you can put on a function that makes it what's called one-to-one. All right? And the definition is up there. If I read the definition, it's just kind of ugly if you read it. But the definition pretty much says that to be one-to-one, this is not okay. Okay, so here this is a function, right? Function, yes. All right, but not one-to-one. I'm going to put 1-1 instead of writing the word one-to-one. One-to-one. Why is it not one-to-one? Well, to be one-to-one says not only does every input have to go to exactly one place, but they have to go to distinct places. You cannot have two inputs go to the same place. So does that kind of make sense why we use the terminology one-to-one? One input, one output, they're matched up exactly, and there's nothing else that goes there. So there's 3 pictures over there on the board, or on the screen there, 3 different examples. I'm going to just jot those down over here so we can see them. So the first example they have there is you have an input, goes to exactly one place. Input goes exactly to one place. Input goes exactly to one place. And each of these come from one place, right? This has only one value associated to it. That's one-to-one. The next example is like the one I just drew over there. You have this goes here, this goes here, this goes somewhere else. This would not be one-to-one, right? So this is I'm going to say function yes, one-to-one yes. Function, is this a function? Yes. One-to-one, no, right? And then look at the last example they have. It goes like this, that, and then it goes like this. Something like that. They only put 2 inputs here. Okay. Is this a function? It's not even a function, because you have one input going to two places, right? So this fails to be a function. Oh, sorry, fails to be a function. As soon as something fails to be a function, you can't even talk about one-to-one. Y'all hear me? In the definition of one-to-one, it says, look at the first two words of this definition. A what? A function is one-to-one if, right? So it would be impossible for me to sit here and talk about one-to-one if it failed to be a function to begin with, all right? It's coming. It's coming. So now we have what's called the horizontal line test. All right. So do y'all remember when we were dealing with functions that an easy way to tell whether or not you had a function was the vertical line test? Remember that vertical line test? So recall again with functions, the vertical line test, VLT, vertical line test. This is a test to see if you have a function, right? This is a test to see if you have a function. So the idea was that if I graph something like this, right? That's a polynomial, right? That looks like a polynomial? A polynomial function. Why is it a function? Because it passes the vertical line test. If I draw any vertical line, right? Any vertical line, I never hit the graph more than once, right? So this is a function, for sure. Now, the horizontal line test is what you do to check to see if it's one-to-one. So if I draw a horizontal line, any horizontal line, I cannot hit the graph more than one time, right? If I do, it's not one-to-one. And you can see here, right? If I draw this horizontal line, I only hit once. But if I draw one like this, look, I hit 1, 2, 3 times. Therefore, this is not one-to-one, all right? Getting rid of all my dead markers here. So that's a pretty simple test to run. Would you agree? Okay, so if you think that's easy, let me give you some examples. All right, you're going to tell me whether or not what I draw up here is a function, and then whether or not it's one-to-one. Give you a couple of examples here. So for this one, let's do, how about this? All right, first of all, is that a function? Yes, pass the vertical line test, right? Okay, is it one-to-one? Yes, if I draw horizontal lines, I never hit more than once. So this would also be one-to-one. Next one. How about a parabola? Function? Yes, pass the vertical line test. Is it one-to-one? No, fails. If I come across, I'll hit more than once. Now what about down here? I don't hit it at all. That's okay. It's okay to not hit the graph. If you hit more than once though, ever, then it fails to be one-to-one. How about this one? Oops. How about a circle? It's not a function, right? All right. Time to grow up. All right, function. It is a function, right? No? No, it's not a function. Fails the vertical line test, right? Fails the vertical line test. Is it one-to-one? I'm not even thinking about one-to-one now, right? Because it's not a function. One more. Students usually have no real big issue with this idea. It's very geometric. You can see it. There's no algebra involved, right? How about this one? How about a sideways parabola? It's not a function, right? This fails the vertical line test. So the danger here is that a student will tell me that this is not a function, right? But they'll tell me it's one-to-one. But yes, it does pass the horizontal line test, right? But it's not a function.
Well, it wouldn't match the one-to-one anyway, because x being 1 would have 2 values anyway, so it would go to 2 different places.
X being 1 would go to 2 different places. That's what makes it fail to be a function,
Yeah.
right? It fails to be a function because if you plug in a value of x, it goes to 2 different places. But that doesn't, 1-to-1, right? 1-to-1, you don't even consider once this fails. Like it's guaranteed this won't happen, right?
I was just saying it can't be 1-to-1.
Like on the picture of it. Is that what you're saying? Like,
I was saying if it's one value, it has to only go to one value.
that's right. And we're saying it does this, right?
Yeah.
We're saying it does that. Like a number, an x value goes 2 different places. Okay, got it? Move on. It's pretty straightforward. All right, so right now we're just generally talking about what the idea is of 1-to-1. Next idea. From this concept of 1-to-1, we have this definition of what's called an inverse function. So what I want you to think about is, you know how when we first started talking about functions, I like to think of a function as like a car wash, right? You have this function, you have a car, truck, whatever you want here. That's truck, obviously. Okay, and it goes in here, right? Goes through the function, comes out, right? Still a truck, hopefully, right? That's, yeah, there's my truck. Okay, so the idea of this car wash is that, you know, goes in clean, goes in dirty, sorry. Goes in dirty, right, comes out clean. An inverse function is a function that would basically take that clean truck and put all the dirt right back on it exactly the way it was when it went in, right? Which isn't realistic. But can you imagine the idea that an inverse function should undo whatever a function just did? All right? So is there a way that we can go backwards, right? Is there a way now I can take this car and plug it in, take this truck and plug it into some other function, right? Which we call the inverse of this, and the notation we use is f with a -1. And the thing is, can we come back and turn it into a dirty car? Can we do that for any function? That's kind of the question. What do you think? Let's say I give you a function. Do you think that every function has an inverse, a function that undoes it? What do you think? No? Generally speaking, no? Turns out, no. Okay, it's not. We can't, not every function has an inverse. Some do, some don't, all right? So the question is, what do we need in order to be guaranteed that we have an inverse, right? Well, guess what? If this is 1-to-1, it has an inverse, all right? If this is a 1-to-1 function, then this guaranteed will happen, all right? So one thing that the book mentions, and I'll mention to you also right now, is in mathematics we have problems with notation of things. There's certain areas in math where we use the same notation to mean 2 different things. So like, you know, if I write this down, y'all should already know that this can be a little confusing if you don't know the context of what I mean here. If I write that down, you don't know if I mean like go to the point 1, 2, go up 1, 2, 3, 4, 5 and plot this point, or am I talking about all the numbers between 2 and 5, right? Not including 2 and not including 5, right? This is the same notation for 2 different concepts, right? And the only way you could distinguish between the two is if you knew what I was talking about, right? If I said, hey, plot this point, you would do that. If I said, hey, the solution is this interval, you do this, yes? Well, there's another piece of notation here that's confusing, and that is this -1. Because up to this point, if I wrote something like, I don't know, x to the -1, that's always meant 1 over x, right? Or if I did something like 2 to the -3, that meant 1 over 2 cubed. So a negative exponent always meant drop it down to the bottom, right? That's not what this notation means, okay? This notation, f inverse, does not mean 1 over f. It's not just the reciprocal of f. So just don't confuse that, all right? This is especially going to be apparent to you in pre-cal, the class after this, because you're going to learn the trig functions, and the trig functions wind up having inverses, and the notation we use for this, for those of you who might have seen this already, you learn about this function called sine of x, and then its inverse function is written this way. And so students will make a mistake and they'll think that this means 1 over sine. And that is not the case. All right, so just I'm laying this out right now that this notation for inverse can be a little confusing. All right, so let me back up. What I've said here is that if somebody gives us a function, we're not guaranteed that it has an inverse, unless this is 1 to 1. If it's 1 to 1, it has one. All right? And what that function does is it undoes whatever that does. Or whatever this function does, it will undo it. All right. Now, a little bit about the inverse, all right? So let's say that let's say we have a function and it does have an inverse, all right? So I'm going to put here, suppose we have a function and it is 1 to 1, which means it has an inverse. Let's discuss the graphs. We're going to talk about what the graphs of these functions are going to have to be. So the way I'm going to do this is I'm going to just act like we have a function, all right? And let's say this is, I'm going to tell you what f does right here. And I'm not going to give you the actual function. Like, I'm not going to write out what the function is. I'm just going to give you what we call the t-table. So I'm going to tell you right now that when you plug 0 into this function, it spits out 3, all right? When you plug -1 into this, it spits out 2. When you plug in 4, it spits out -2. And when you plug in, let's say 7, it spits out 6. Okay, I'm telling you, you're trusting me, that this table represents values from this function, which is 1 to 1 and has an inverse, right? What I'd like to ask you is, what does the inverse function, what does the table for that do? So remember, this is the input, this is the output, right, for this function. This is like the truck going in dirty, coming out clean. Dirty, clean, right, dirty, clean. Input, output. What should the inverse do? It undoes it, right? It undoes what f just did. So what should it do with 3? It should take that 3 back to 0, right? It should take 2 back to -1. It should take -2 back to 4 and 6 back to 7, right? It's just going to send everything back to where it came from. Now let me ask you this. Do I know what it does with 0? According to the information you have in front of you, do you know what this function does with 0? Well, all the inverse is going to do is take these outputs back to where they came from, right? Well, I don't know anything about 0, do I? So I don't know where it came from. So I would not be able to answer this right now. The only thing I can tell you is that if you tell me this is what f did, I can tell you that's what the inverse is going to do. Understand?
So would a linear line just be the same thing?
A linear function would, well, a linear function, what do you mean the same thing? Would it be the same line?
Since you plug in 1, you get 1. Like a regular x.
Oh, you're saying like y equals x, the identity function, right? That special one? Its inverse would be the same, itself, exactly. We're actually going to see that, yes?
If it's not 1 to 1, can it also be in some cases, can it in
some cases have an inverse?
So if it's not one-to-one, there are workarounds. But the workaround is that you have to usually do what's called a domain restriction. So you have to restrict the domain so that in that little region, it is one-to-one. And that's what you do in pre-cal when you deal with those trig functions. And we're going to do one. It's, I think, our last example. We're going to do a problem where we have to restrict the domain in order to have an inverse. All right, so let's take a look at this. I want to look at this in more detail. Okay, what I'm going to do here is I'm going to try and draw this to the best of my ability. I'm going to plot some points. So I'm going to first look at the points that live on this function f. 0, 3. Do y'all agree that's 0, 3? Right? Okay, next one is negative 1, 2. It's there, right? 4, negative 2. Here. And then 7, 6. So 4, 5, 6, 7. Here's 7. Go up 6. 1, 2, 3, 4, 5, 6. All right. Those are the 4 points I gave you, right? That live on this function f. Now we're going to look at the 4 points that live on the inverse. So this is the x, this is the y. This is x, y, x, y, x, y. So 3, 0 would be 1, 2, 3, that's here. Then we have 2, negative 1 to the right, 2 down 1. And then negative 2, 1, 2, and up 4, 1, 2, 3, 4. And then finally we have 6, 7. 1, 2, 3, 4, 5, 6, and then up, that was 6, so 7 right there. Okay, there we go. Now, there's a relationship between these, okay? And if you've never seen it before, it's kind of hard to see here. What I'm going to do is I'm going to connect the greens together with straight lines. Even though we have no idea if this function is straight lines, I'm just going to do it to help us see it. If I connect the green dots together like connecting dots like back in grade school, if I do that, and then I do the same thing with the red ones. That might help you see it. Do they look kind of like they're the same a little bit?
Yeah.
But you have to do what? Tilt your head over like this. And remember, you know how like when we were talking about functions and we were talking about reflections over the y-axis, reflections over the x-axis? Do you all see that if you tilt your head and you draw an imaginary line that goes right through the middle, like 45 degrees, do you see that they look like it's a mirrored image of itself over that line? You all see that? That is a property of a function and its inverse. When you graph them together, they will always be reflections over that diagonal line. Now that's what that note says right there. Do you see that? That's what it's saying. If the blue one is the function f and that purplish red one is the inverse, when you graph both of them, then if you draw that diagonal line, which, by the way, this diagonal line is y equals x. That's the diagonal line. It's one of our toolbox functions. We're supposed to know what it looks like. If you draw y equals x, then f and its inverse will be reflections over that line. Okay? And that's why, what you were just saying, what about that function itself? Right? Does it have an inverse? Well, draw it, and then what would the reflection of it be? Itself, right? So this function is its own inverse. Okay, let's recap. Let's just recap because we're about to get into the algebra part of this. Everything here has been visual. So if we have a function, right, it may or may not be one-to-one. If it's one-to-one, then it has an inverse. If we draw the inverse in the original function together, they are reflections of each other over the identity. That's what we call that diagonal line, the identity. That's where we are. So now, how do we check If somebody gives us a function, right? Let's say somebody gives us a function, and then they tell us, hey, everyone, like they tell you, hey, this function, they give you two functions, I should say it that way. They give you two functions, they say, hey, they're telling you this function and this function, they're inverses of one another. How can we check that? Check to see if that's true. And I'm not talking about graphing, I'm talking about algebraically. So let's do an example here. So if you're given, let's see, I'm gonna do, okay, I'll do that one. So I'm gonna verify, this is example 4 here. I wanna verify that these are inverses. All right, so the function, the first function they give us is g of x is x cubed. And then the other one, they're telling us that g inverse of x is the cube root of x. Now, all my markers are dead. We need to verify that those are inverses. We're being told they are. We need to check. So think about it this way. Let's look at G real quick. And by the way, what I'm doing right here is not how we verify. I'm just trying to get us to think about it. What does G do? Let's take some numbers here, making a little t-table. Let's plug 0 into G. What is G spit out? Plug 0 into here. 0 cubed is 0. Okay. Let's plug in 1. What's 1 cubed? 1. 2, 8, right? Maybe one more. 3, 27, right? 3 times 3 times 3. Right, that's what G does. All right, let's take a look at that inverse. Does it undo these? Does it send these back to where they came from? So what I'm doing is I'm going to take these numbers here, put them here, 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 and here. And I'm going to see, does this go back to 3, go back to 2, go back to 1, go back to 0? So now you're taking these and plugging them into the inverse. What's the cube root of 0? 0, right? What number times itself? 3 times is 0. What's the cube root of 1? 1. Cube root of 8? 2. Cube root of 27? 3. Do you see it does look like it's the inverse? Do you have questions on that? Sure? Okay, but this is not the way we verify. We don't just pick a few points and say, yeah, because in order to say it's the inverse, you would have to check every point. And there's no way to check every point, all right? So what I want you to do is think of it this way. This will lead us to where we're going. If I plug in an x here, right? If I plug in x here, what should come out here? Some y value, but it's getting plugged into g, right? So g of x should come out here. Do you all agree? If I plug x in here, g of x comes out. Yes? Now, if I take that answer, g of x, and I plug it into what? That? How do I write that? I'm plugging this into this. This is what we did last class. This is composition. G inverse, what goes into it? This. What does that answer need to be in order for this to be true? This needs to go back to x, right? So if x goes into g, becomes g of x. If this is the inverse, then when I take that g of x and I plug it in here, which is composition, it better spit out x. It better take it back to where it came from, right? And so this is what I need to check. This is the check. You have to check that this is true. Yes? No, you have to use x. You can't pick a number. You have to use the arbitrary value x, the variable x.
I thought it was one of the x values.
Now, look at where it says here, verify the inverse. I'm going to make that bigger. Now, on this verify the inverse, do you see that they're using f instead of g? Is that all right with you? Do you see the first one there? The first thing it says we have to verify, in order to verify that two functions are inverses, The first thing we have to verify is that when you take the inverse function and plug the other function into it, you get x. But do you see we have to check a second thing? See that second thing? The second thing we have to check is that it works the other way as well. In other words, if we were to start with an x here, okay, let me do it, I'm trying to squeeze it in here. If we were to start with an x here, it would go into this function and become what? G inverse of x, right? I'm sorry, of x. Now, if we take that G inverse of x and plug it in over here to this function, it goes in through that function and becomes what over here? G inverse goes inside of G of x. And what should that come out to be as well? Y'all aren't seeing this one, are you? Y'all aren't seeing this, are you? I'm going to draw a different way. Draw a different way. Okay, let's try it this way. I want to do this one first. Okay, the one, I think most of y'all understood that, right? Yes? So the first thing we did to verify is that if this is G, right, then we plugged in x, it goes through here, it becomes G of x. Now, the inverse function should send it back, right? The inverse should send it back. So when you plug that into this, right, when you plug that into this, you should get G inverse of G of x. Right? That's what happens when you take that and plug it in through here, and that needs to be equal to that. So these two have to be the same. What I tried to show here in green is this scenario. What if we start, if this is G going here, and the inverse takes it back, what if we start with an x here? That x is going to go through, right? And it'll become G inverse of x. And now send that back through with G. So send it back here, and that's G of G inverse of x. And what does that need to be? X. I hope that makes a little more sense. So there are two things we have to check. We have to check when you do, the first one says when you put the original function into the inverse, it just spits out x. And the second one says when you put the inverse into the original function, it spits out x. All right, so let's do this problem. This was just me trying to convince you as to what we need to do. So to verify that these are truly inverses, here's the first thing. First thing I have to show. I want to show that G inverse of G of x must equal x. That's what I need to show. So this we learned to do last class, right? Oh, I forgot the little -1 there.